let's have a look at another example of computing a definite integral. So let's compute this integral, the integral from 0 to 4 of 1 minus x dx. And when we're done, let's interpret it as an area. So just for practice, I want to compute this integral using the limit of a Riemann sum definition of the definite integral. So this is the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I times delta x. And so the function is the 1 minus function, so 1 minus. And now we need to write x sub I, which, remember, x sub I is the bottom bound, which is 0, plus I times delta x. And delta x is 4 minus 0, so 4 over n. And here's delta x again, so 4 over n. All right. So to evaluate this sum, maybe we could start by moving this factor of 4 over n outside of the sum, and then simplify the stuff that's left over in the sum. So limit as n goes to infinity of 4 over n times the sum from I equals 1 to n of, looks like we've got 1 minus 4i over n. Now remember, one property of this sigma notation is when you have a sum or a difference inside of your sigma, you can sort of distribute the sigma. It's not really distributing the sigma, it's using the addition and commutativity, the associativity and commutativity of addition to rearrange the sum, but it kind of looks like you're distributing the sigma. So we get the sum from I equals 1 to n of 1 minus the sum from I equals 1 to n of 4i over n. All right, now on this, I'm missing a closing bracket here. There we go. Now on this second sum, this factor of 4 over n, that doesn't depend on I, so this 4 over n is a common factor in this sum, so we can factor it out by moving it outside of the sigma. And now everything that's left over in a sigma is something that we have a formula for. So this is the limit as n goes to infinity of 4 over n times the sum from 1 to n of 1. Well, that's just adding 1 to itself n times, and that gives you n minus 4 over n. Okay, now this piece, the sum from I equals 1 to n of I, there's a nice formula for that. And that was n times n plus 1 over 2. All right, so now we've evaluated the sums. Now we need to maybe simplify this and then evaluate the limit. To simplify this, I think what I'm going to do is distribute this 4 over n. I know I factored it out a minute ago, but now I want to distribute it. So limit as n goes to infinity of, let's see, 4 over n times n, that's just 4, minus, and then 4 over n times 4 over n is 16 over n squared, times, I'm going to multiply out this n times n plus 1, so that's n squared plus n over 2. Now I can get rid of a factor of 2 here. This gives me an 8 there, and this 2's gone. And let's see, let's gather up our n's here. So limit as n goes to infinity of 4 minus 8 times n squared plus n over n squared. And that looks familiar. Now how to handle that, just do the division. 4 minus 8 times, so n squared over n squared is 1, plus n over n squared is 1 over n. And let's see, as we take a limit, 1 over n goes to 0. So we're left with 4 minus 8 times 1, so 4 minus 8, and that's negative 4. But wait a second, negative 4. Remember this integral that we were calculating, the integral from 0 to 4 of 1 minus x dx, we said that this was an area. So let's draw a picture of this region Maybe we can figure out why this came out to be negative. So if we graphed the integrand here, so we're going from x equals 0 to x equals 4. And 1 minus x, let's see, that's going to look something like about this. Y-intercept is at 1, and then it goes down like this. And what you can see is that the region between the graph and the x-axis, it's made up of these two triangles, one small and one big. A lot of the area here is actually extending below the x-axis. And that matters because, right, if you write out the limit definition of, well, let's write out the limit definition of this integral, limit as n goes to infinity of the sum of f of x sub I times delta x, right? In this region where the function is negative, right, all of these x values here, all of these function values, these are going to be negative for these red spots, right? So essentially, remember, an integral adds up a bunch of infinitely small areas, and all of these areas are the height times the width of these slivers, but these red slivers, since they're extending below the x-axis, their height counts as negative. So the area that is below the x-axis will also count as negative. And that kind of explains why we came up with a negative area here. It's because there's more area below the x-axis than there is area above the x-axis. So, when we originally wrote down the definition for this integral, we kind of intended to write down something that would give us the area. But what this actually gives us is the, maybe you could call it the net or the signed area between the graph and the x-axis. And when we say the signed area here, the net signed area, area above the x-axis counts as positive, and area below the x-axis counts as negative. So the reason we came up with a negative 4 for the area is because there's more negative area than positive area, and so the negative area wins and you end up with a negative. In fact, since these are both triangles, we could work out the signed area just using the area formula for triangles. So we could have the positive area plus the negative area. Okay, now the positive area is going to be coming from this little triangle that's sitting above the x-axis. This little triangle is 1 unit horizontal and 1 unit vertical, so its area is 1/2, the base is 1 and the height is 1, plus, and then the other triangle is going to count as negative. It looks like its base is 3 and its height is also 3. So 1/2, 3 times 3. So this is going to give us 1/2 minus 9/2, which is negative 8/2, which is negative 4. And that's what we got before. So this sort of verifies that, yes, indeed, this integral gives you a net area or a signed area, not an absolute total area. That may seem strange at first, that may seem like a problem, but we'll see in applications that usually what you want is the net area. So it's good that our definition gives us the net area. All right. So this definite integral does give us a net signed area. If you actually want a total area and not a net signed area, that's easy to do. All you need to do is make sure that your integrand is never negative. And to do that, just throw some absolute value signs around it. That's an easy enough thing to do. So for an example of that, let's find the value of the integral from -2 to 4 of the absolute value of 2x. So if we look at the region that we're finding, finding the assigned area of here, right? The absolute value of 2x is going to look something like this. And you can see that that absolute value has forced all of this area, all of the area between the graph and the x-axis to be positive area instead of negative area. If it had just been the integral from -2 to 4 of 2x dx, well, that would look like this, and some of the area down here would count as negative. But that's not what we have here. The absolute value has flipped the negative area up, so it counts as positive area. And now we just need to find out how much positive area there is here. It looks like we're going to get triangular regions again, so let's just use the triangle, the area formula for a triangle. Let's see, we're going to go from -2 to +4. Right? Because of the 2 here, since the width of this triangle is 2, the height is going to be twice that, which is 4. And then for the triangle on the right, the base of that triangle is 4, and that means its height is going to be twice that, which is 8. And so now we can work out the area of these triangles. So the area on the left is 1/2 times the base times the height, so 1/2, 2 times 4. The area on the right is 1/2 the base 4 times the height 8. And now we can just do this calculation here, right? Simplify everything. 4 plus 16, that's 20. And so this integral turns out to be 20. All right, I think this is a good example of where it can pay to remember that what an integral is calculating is some kind of area, because it can give you shortcuts for calculating that area. If we had tried to use the limit definition to calculate this integral, we could have done it, but it would have taken a lot more work than this.